Hello everyone, this is Jiaxin. We are from Into the AI Research. Today we are so happy to present our recent work about the document enhancement using cycle-consistent diffusion models. So this is the collaborative with Joy, Lalla, Kamalika, and Kumar from Into the AI Research. So as we know, for our TurboTax product, we have a bunch of different type of text forms, right, in a document. And before we put it to OCR, we have additional step to clean and enhance the document quality. Typically, we have different type of issues like the noise document and some shadow and the watermarker. And here, this figure shows the typical document enhancement task, including denoising, shadow removal, bannerization, watermarker removal, deblurring, and defade. Let's give a brief overview of the existing work. So we classify this kind of measures based on their mechanism. Is a paired or unpaired, or the different type of backbone models like GAN, CN, transformers. And also we want to say these measures will cover different type of document enhancement tasks. As I mentioned, the six typical tasks. And from this table, we can see that most of the measures are based on paired supervision. That means you need the input and the corresponding output. In other words, for the noise document, you have to have the clean document as the paired supervision. And only there are two measures is unpaired supervision from ACCV and SCCV 2021. But they use the GAN model as the backbone and to just cover part of the tasks in the typical 6 tasks. What we want to do is also focus on the unpaired supervision. So based on the recent advances from the diffusion models, we propose this kind of cycle-consistent diffusion models. The basic idea is want to transfer the noise document as the source data or source distribution and convert to the latent space. And then we want to have the inverse diffusion process to decode to get the target clean document. So this process is typically like the figure shows, we start from the original source distribution and want to map it to the target clean distribution. And here we will have to train 2 diffusion models and operate in the latent space to achieve this goal. This is our basic algorithm. So our method consists of 2 parts. One is the training part, and another one is the translation part. So for the training part, we typically require the noise data from source domain and the clean data from the target domain. And also because many private document where it's like financial, the document is pretty sparse, we have additional step for data augmentation to get more and more data. And this is the second step, we perform the data augmentation. And after that, we want to train source diffusion models and the target diffusion models separately. And we will get this source model and a target model. For the algorithm 2 is the unpaired image translation. So for that part, we need just some sample from the source domain, and because we have the pre-trained model, so we have the source model and target model. And the first step is to encoding. That means obtain the latent embedding from the source domain data using the DECDM diffusion model. And once we obtain the embeddings, we can execute the decoding part. That means we can obtain target domain data reconstructed from the latent code. And using this process, we can perform like from the noise data, transfer the noise data to the clean data. Here we want to show a synthesized example. So this is 2D images and some distributions. And you will see like this is source distribution, and we encode it to the latent space and the decode get the target space. That means we want to map the source distribution to the target distribution. So imagine for the images or document is a very high dimensional case, but for that one it's just a 2-dimensional case. So we can exactly map from your source distribution to the target distribution, no matter how complex or how different from both. Here we want to demonstrate our proposed methodology on the real-world tasks. For example, the first one is the dirty document cleaning. Means we have some noise data and the noise document, and then we will use our methods to get the good performance, to get a clean document, and compare with some other methods like your former transnonide and the inverse DN. Most of them are based on the pair, the supervision as I mentioned in the beginning. And also some of them rely on either again backbone or transformer backbone, but compare them, our method performs very competitive, but we just need unpaired assumption. So, and this one is the shadow removal tasks, and we also compare with our methods with other baseline methods and see we have a good performance and without any assumption of the paired supervision. A quick conclusion is we propose the DECDM, entry-end document level image translation methods inspired by recent advances in diffusion models. So our methods overcomes the limitation of a pair training by independently training the source model and the target model, make it possible to apply domain-specific diffusion models to other pairs. And our proposed DECDM trains on the dataset at a time, eliminating the need to scan both datasets concurrently and effectively preserving data privacy from the source to target domain. We also introduced this simple data augmentation strategies to improve the performance during translation. Finally, we compare our methods with the state-of-the-art methods on multiple synthesized data and the benchmark datasets, such as the document denoising and the shadow removal, and demonstrate our good performance quantitatively and qualitatively. Okay, that's it. Thank you.